Hello students, welcome to this video lecture on System of Particles and Rotational Motion Part 2 given in chapter number 7 of Physics for Class 11. Today's video lecture will start with vector product of two vectors, which is helpful in understanding the physical quantities like angular velocity, linear velocity, torque, angular momentum. The discussions of today's lecture are very descriptive and needs a lot of attention. Hence, I request you to listen it very carefully, note down all the important points, and wherever I am going fast, please pause, go back and replay. Note down the important points. I welcome you once again. Vector product of two vectors. A vector product of two vectors A and B equal to C, that is written as C is equal to A cross B. Please note cross. C is equal to A cross B, where C is a vector in a direction perpendicular to A and B, and it is this product is also known as cross product because of cross sign. The vector product of two non-zero vectors A and B is defined as A cross B is equal to magnitude of vector A into magnitude of vector B sin theta into n hat n. Here A is a vector, B is a vector, and their cross product is A cross B, and theta is the angle between vector A and vector B, and n is a unit vector perpendicular or normal to A and B, plane containing A and B. Theta lies between 0 and pi radians. That is, theta is greater than 0 but less than pi, and n is the unit vector perpendicular to both A and B. Vector A, vector B, and vector normal form a right-handed system. The right-handed system rotated from A to B moves in a direction of n. Consider a right-handed screw with its head lying on the plane of A and B as shown in figure A, and the screw perpendicular to this plane. This screw is perpendicular to this plane. Then if we turn the head, this head of the screw, if we turn direction in the direction A to B, then the tip of the screw moves upwards, that is moves in the direction of vector C. This is the right-handed screw rule, and it is shown in the figure above. This can also be understood using the thumb rule. If one curls up the fingers of the right-handed around a line perpendicular to the plane of vectors A and B. Here you see the figure B, A and B are two vectors which meet at an angle theta. If one curls up the fingers of right-handed around a line perpendicular to the plane of vectors A and B, and if the fingers are curled up the direction from A to B, then the stretched thumb, this thumb represents in the direction of C. The thumb is in the direction of C. Please see the figure C also. In figure C, it is illustrated, vectors A and B are illustrated more clearly. The angle between A and B is theta. So, if you move from A to B, the direction of motion or rotation is vertically up. Whereas, if you move from B to A, the direction is negative, minus n. This is the right-handed rule. If either A equal to 0 or B equal to 0, then theta is not defined. So it is applicable only for non-zero vectors. If A equal to 0 or B equal to 0, then A cross B is 0. There are some more properties. As we have said earlier, A cross B, that is magnitude of A cross B is equal to magnitude of A into magnitude of B into sine theta. From this relationship, we can find out sine of theta. Therefore, sine theta is given by sine theta is equal to magnitude of A cross B divided by magnitude of A into magnitude of B. If A and B are two non-zero vectors, then A and B are parallel. Parallel or collinear if and only if A cross B is 0. So that means the vectors become parallel if A cross B is 0. And there are further properties of a null vector. There is a special vector called null vector which is defined as A cross A. That is vector product of the vector itself. That is A cross B equal to 0. Similarly, we have I cross I is equal to J cross J equal to K cross K equal to 0, where I, J and K are the unit vectors in the direction of X, Y and Z. And one more relation is I cross J is equal to K and J cross K is equal to I and K cross I equals J. I, J, K are unit vectors and represented by a cap or a hat on their head. Properties of vector product. Property number 1. The vector product under reflection. A cross B can also be written as within brackets minus vector A cross minus vector B. That becomes minus into minus plus A cross B. Distributive property. We know for the dot product A dot B plus C is equal to A dot B plus A dot B. In the same A dot C, in the same fashion, we can write the cross product. That is A cross B plus C is equal to A cross B plus A cross C as shown here. Then vector product in determinant form. For simplifying and for easy calculation, we write the vectors to vector product in determinant form as shown below. So consider two vectors A is equal to A1i plus A2j plus A3k and B is equal to B1i plus B2j plus B3k. Then the vector product vector A cross vector B can be written as determinant ijk in first row, where I, j, k are the unit vectors and the coefficient of the respective units in the unit vectors in the second row, that is A1, A2 and A3. And in the third row, we write the coefficients of the unit vectors in the third row, the B vector, vector B, B1, B2, B3. Hence, we can simplify using the determinants principles. Let us take one example to understand the scalar and vector products of two vectors. Let A be equal to 3i minus 4j plus 5k and B is equal to minus 2i plus j minus 3k. Now, two vectors are given. Now, we will find the first step, the scalar product or dot product. Therefore, vector A dot vector B is equal to 3i minus 4j plus 4k into dot minus 2i plus j minus 3k. So, multiplying we get minus 6 minus 4 and minus 3. That is I dot I is equal to 1, 2 into 3 is 6. So, simplifying we get minus 25. Now, we will find the vector product by writing A cross B equals determinant ijk in the first row, then writing the coefficients of vector I, that is 3, -4 and 5. These are the given. And in the third row, we write the coefficients of unit vectors of vector B, -2, 1 and -3. Simplifying, we get 7i minus j minus 5k. This is simplified using the determinant principle. So this is the difference between two vectors. Now next we will study about the angular velocity and its relation with linear velocity. In rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle. Consider the body here. This is a body, and every particle of this body moves in a circle because of rotational motion. It is rotating, which lies in a plane perpendicular to the axis and has its center on the axis. So every particle, the center of this rotation lies on the vertical axis, perpendicular axis, and has center on its axis. The figure above shows a particle P of the rigid body which rotates about the fixed axis. That is, the fixed axis is Z. So please note here how to write this diagram, how to copy. First draw three coordinates, coordinate X, coordinate Y and coordinate Z. This is coordinate Z. All the three are mutually perpendicular to one another and meet at the origin O. Here they meet as shown in the diagram. Then you select any center of the circle C and select a point P at a distance R from the center C. The C is on the Z axis and mark a circle. This is the circular motion of the particle. The tangent to this point P is the velocity, linear velocity, and the particle moves from to P dash at a making an angle delta theta for a rotation during delta t. The figure shows the linear velocity vector v of a particle at P. It is along the tangent P of the circle. Let P dash be the position of particle after an interval of time delta t. The angle, this is the angle P dash CP, describes an angular displacement. The angular delta theta is the angular displacement here of the particle at time delta t. The average angular velocity of this particle over time interval delta t is given by delta theta by delta t. So average angular velocity, please remember, is the ratio of delta theta by delta t. To find the instantaneous velocity, we have to take the limit of this ratio. Therefore, limit of delta theta by delta t as delta t tends to 0 is given by d theta by dt. Please write it very carefully. Know the difference between delta theta and dt. Therefore, the ratio d theta by dt is an instantaneous angular velocity of the particle P at position P. We denote this instantaneous velocity by letter omega. This is the Greek letter omega. Therefore, d theta by dt is equal to omega. For any perpendicular distance Ri, here we have considered R, any other particular in a circular motion Ri from fixed axis, the linear velocity at a given instance Vi is given by the relation Vi is equal to omega I Ri. Here Vi is the linear velocity and omega I is the angular velocity and Ri is the displacement. Here the subscript I varies from 1 to n. Some important points regarding angular velocity. The figure A shown in the right hand side is repeated from the previous slide. X, Y, Z are three coordinates meeting at the origin O. Z is a fixed axis and C is a point on this fixed axis. A particle P makes a rotational motion shown in circular manner shown in the dotted lines. V is the tangent, that is the linear velocity, and the point P moves to point P dash in a time interval delta t and makes an angle delta t. R is the position vector and omega is the angular velocity as shown in the figure. Angular velocity following the right hand momentum. Right hand rule. For particles on x-axis, r is equal to 0. If there is any particle lying on this x-axis, the distance r is 0. Hence, the velocity, linear velocity v is equal to omega r equal to 0. Thus, the particle on the axis is stationary. Omega is the angular velocity of the whole body. This omega is the angular velocity which is perpendicular to the plane or perpendicular to the circular motion and is the velocity of the whole body. In pure translation of a body, translation motion of body, all parts of the body have the same velocity at any instant of time. Similarly, in pure rotational motion also, all the parties of the body move in the same angular velocity v at omega at any instant of time. Each particle of body moves in a circle as shown in the figure, which lies in a plane perpendicular to the axis of rotation and has the center on its axis. This is shown here in the figure below also. This is the direction of rotation and the axis, fixed axis is shown here in the marked arrow, and the direction of omega depends and follows the right hand rule. Omega is shown here, the direction of the arrow. The angular velocity is a vector. See, omega is a vector. For rotation about fixed axis, the angular velocity vector omega lies along axis of rotation and points out in the direction in which right-handed screw would advance if the head of screw is rotated with the body. Angular acceleration. You are all familiar with kinetic variables of linear displacement and vector velocity vector in translational motion. In rotational motion, we use physical quantities such as angular displacement theta and angular velocity omega. Both are vector quantities. Similarly, we also use the concept of angular acceleration in analogy with linear acceleration, which is defined as time rate of change of velocity in translational motion. Here, in rotational motion, we define angular acceleration vector alpha as the time rate of change of angular velocity omega. Thus, angular acceleration vector alpha is equal to d omega by dt, that is rate of change of angular velocity. Let it be equation 1. If the axis of rotation is fixed, the direction of omega and hence that of alpha is fixed. In this case, that is, when the axis of rotation is fixed, the vector equation reduces to an scalar equation. Hence, we remove the vector sign and simply write alpha is equal to d omega by dt. This is angular acceleration. Torque and angular momentum. The theory part of torque is explained using the figure as shown on the right hand side of your screen. Here x, y and z are the three mutually perpendicular axes meeting at the origin O. R is a position vector of length OP. P is a particle on the body in the body. A force F acts at an angle theta on R as shown in the figure. The vector F is projected backwards so as to meet a perpendicular right from the origin as shown in the figure. The perpendicular line is perpendicular distance from origin is r sin theta. And we can also draw a F perpendicular F sin theta perpendicular to vector r. Though it is not shown in the figure, you can draw from this side. Now we will proceed to define and explain the torque. Torque and angular momentum are two physical quantities which are defined as vector product of two vectors. These are important in the discussion of motion of systems of particles, particularly the rigid bodies. Moment of force or torque. Moment of force or torque is represented by a Greek letter tau, T-O-W. Consider a position vector r acted upon by a force F inclined at an angle theta as shown in the figure which I have already explained. We use the term force in linear motion, whereas in rotational motion the term used is moment of force, which is analogous to the force. It is also referred to as a torque or a couple. The moment of force acting on the particle with respect to origin O is defined as vector product vector tau is equal to vector r cross vector f. This is the cross product or the vector product. So vector tau is equal to vector r cross vector f. Let it be equation 1. This tau is shown in the figure. This is the tau which is perpendicular to both the position vector r as well as perpendicular to vector f. The magnitude of the moment of force is tau and which can be written as tau is equal to r into f sin theta. This is from our basic knowledge of vector product using magnitudes. Let it be equation 2. Therefore, the equation 2 can be rearranged as tau is equal to r sin theta into f, that is equal to r sin theta is the perpendicular r perpendicular into f. Let it be equation 3. So r sin theta is replaced by the letter r perpendicular. Similarly, we can arrange equation 2 as tau is equal to r into f into sin theta. That can be written as r into f sin theta is f perpendicular. Let it be equation 4. Here, r perpendicular is equal to r sin theta is a perpendicular distance of f from the origin. This is shown, r sin theta is shown in the figure. And f perpendicular f equals f sin theta is component of F. So we can draw a perpendicular line from point F to vector R projected direction of F, which is F sin theta. Here the vertical line will be F sin theta is the component of F in the direction perpendicular to R as shown in the figure. There are certain important points about the torque or the moment of force. The moment of force or torque is a vector quantity. Second point, the magnitude of tau is equal to R into F sin theta, which is explained in equation 2 here on the left hand side. The moment of force has dimensions m, capital L square t to the power of minus 2. Moment of force is a vector while the work is a scalar. The SI unit of moment of force is Newton meters. Angular momentum of a particle. Just as the moment of a force is the rotational analog of force in linear motion, the quantity angular momentum is the rotational analog of linear momentum. That means angular momentum in rotational motion is analogous to linear momentum. We shall first define angular momentum for the special case of a single particle and look at its usefulness in the context of a single particle motion. We shall then extend the definition of angular momentum to the system of particles, including rigid bodies, which we are going to explain in subsequent slides. Let us start with angular momentum. The quantity angular momentum is a rotational analog of linear momentum. Angular momentum is a vector product. It could also be referred as moment of momentum. Please underline moment of momentum, that is moment of linear momentum. Consider a particle of mass m and linear momentum vector p at a position r relative to the origin O. The angular momentum vector L of the particle with respect to origin O is defined as vector L is equal to R cross P, where L is the angular momentum, R is the position vector, and P is the moment. Let it be equation 1. The magnitude of angular momentum vector is given by the relation L is equal to R into P, Rp sin theta. Let it be equation 2. This we have obtained from the knowledge of vector algebra using magnitude relationship. Here P is the magnitude of vector P and theta is the angle between vector R and vector P. We may write angular momentum L is equal to Rp perpendicular or L is equal to P into R perpendicular. This form is already expressed in the previous slides using representation for perpendicular force and perpendicular position vector. Here R perpendicular, which is equal to R sin theta, is the perpendicular distance of directional line of P from the origin, and P perpendicular, which is equal to P sin theta, is the component of vector P in the direction perpendicular to R. The angular momentum is 0, that is L is equal to 0 if the linear momentum P equals 0, or if the particle is at the origin R equal to 0, or if the directional line of P passes through the origin theta is equal to 0 degrees or 180 degrees. That means angular wave momentum will be 0 because of three conditions. That is, linear momentum P could be 0, or if the particle is at the origin, that is R equal to 0, or if the directional line of P, vector P, passes through the origin theta equal to 0 or theta equal to 180 degrees. Next point, the physical quantities moment of a force and angular momentum have an important relation between them. It is the rotational analog of relation between force and linear momentum. Remember that, which we are going to explain mathematically in the next slide. Angular momentum and torque. For deriving the relation in the context of a single particle, differentiate the equation L is equal to R cross P. We have already established the relation between angular momentum, position vector, and linear momentum. Therefore, L is equal to vector R cross vector P with respect to time. We have to differentiate this. Therefore, differentiating this equation, we get dl by dt is equal to d by dt of vector R cross vector P. So using this is the differential of two vectors. It is given by, from the knowledge of our calculus, we get the differential of the first u, that is dr by dt cross P plus R into differential of P. Therefore, d by dt of R cross P can be written as equals dr by dt cross P plus vector R cross dp by dt. This you have to remember because we have used the knowledge of differentiation. Next point. Now the velocity of particle is given by the relation vector v is equal to dr by dt. We already know that vectorially the velocity can be written as dr by dt, that is the rate of change of displacement. And we also know that vector p is equal to m into v. Therefore, we get dr by dt cross p equals, we can write dr by dt is vector v and p is given by the relation m into vector v. So here we get v, if you take m as a constant outside, we get m into v cross v, and we already know that when we multiply the vector by its own another vector, that is v into v cross v is 0. Therefore, the first term in this equation becomes 0 as the vector product of two parallel vectors vanishes. Further, dp by dt now we have in this equation 1, we have dp by dt. dp by dt, that is differential of momentum is force F, a force vectors F. Therefore, R cross the second term in the equation 1 can be written as R cross dp by dt is equal to R cross F, and this is R cross F is tau by definition. Thus, the time rate of change of angular momentum of a particle is equal to the torque acting on it. This is the rotational analog of equation F is equal to d by dt of vector p, which expresses Newton's second law of motion for the translation motion of a single particle. That is, the relationship F is equal to dp by dt is the Newton's second law of motion for a single particle. Now we will take up torque and angular momentum of a system particle. In the previous slide, we studied about torque and angular momentum for a single particle. Now we are extending it to a system of particles, that is to a rigid body. To get the total angular momentum of a system of particles about a given point, we need to add vectorially the angular momenta of individual particles. So, that is, since we already know about a single particle, now we have to sum up vectorially, that is, add vectorially angular momentum of individual particles. Let us do it. Thus, if there are n particles in a system, we can write capital L, that is summation of all particles, vector L, capital L is equal to L1 plus L2 plus etc. plus Ln, where L1, L2 up to Ln are all vectors of individual particles of 1, 2, etc. up to n respectively. These terms, multiple terms, can be written as summation, algebraically summation sigma I equal to 1 to n of Ln, where n varies, I equals 1 to n. I varies from 1 to n. Let it be equation 1. The angular momentum of ith particle is given by the relation Li is equal to Ri vector Ri cross vector Pi. Let it be equation 2. That is, Li is equal to Ri cross Pi, where L, R and P are vectors, where Ri is the position vector of ith particle with respect to a given origin and P equals Mi into Vi, the linear momentum of the particle. So, equation 2 is, right hand side is for linear momentum, left hand side is the angular momentum. Therefore, the total angular momentum of the system of particles capital L, vector capital L is equal to summation I equals 1 to n of Ln. That can be written as sigma summation of I Ri vector Ri into vector Ri cross vector Pi. Let it be equation 3. This is the generalization of definition of angular momentum for a single particle to a system of particles. That means we have used, we have first understood for the definition of angular momentum of a single particle and converted it into a system of particles. Hence, differentiating, we get differentiating equation 3, we get dl by dt equals d by dt of sigma li. So where capital L and small l both are vectors. That can also be written as sigma I into dl by dt. That means we have taken the summation sign outside. So that can be written as sigma I of tau I, because dl by dt is tau I. Let it be equation 4, where tau I, vector tau I is the torque acting on the ith particle. Therefore, tau I, vector tau I is equal to vector Ri cross vector Fi. Thus, the force Fi on ith particle is the vector sum of external forces acting on the particle and the internal forces Fi internal ex exerted on it by the other particle of the system. We may therefore separate the contribution of external and the internal forces to a torque. That means tau is equal to sigma I of tau I, vector tau I is equal to sigma I of Ri cross Fi. The tau itself can be due to internal forces as well as external forces. Here in equation 5, tau internal is equal to sigma of I Ri vector Ri cross Fi internal, where F is the internal force, and tau I equals sigma I of Ri cross Fi external. So it is first here, this is internal and this is due to external. Now let us consider where internal tau I is equal to 0. Then tau I is will, if tau I in this equation is 0, then tau will be equal to only due to external forces. Therefore, tau will be equal to tau external. And dl by dt, that is differential of angular momentum, will be equal to tau external. Let it be equation 6. Note, when we have only one particle, there are no internal forces or torques. Therefore, tau I will be equal to 0. The above equation 6 holds good for any system of particles, whether it is a rigid body or its individual particles have all kinds of internal motion. Conservation of angular momentum. Consider a case where tau external equals 0. Then the equation d by dt of vector L equals tau external. That is, the torque is only due to tau external, which reduces to dl by dt, because tau external equals 0, dl by dt will be 0, or the total angular momentum L will be equal to constant. That means from the knowledge of our differential calculus, if the differential is 0, that means the parameter here L is a constant. That is, differential of a constant is 0. Therefore, L is a constant. Let it be equation 7a. Thus, if the total external torque on a system of particles is zero, then the total angular momentum of the system is conserved, that is, remains constant. From the above equation 7a, we can conclude that if the total external torque on a system of particles is zero, then the angular momentum of the system is conserved. That means L is equal to vector L is constant. Therefore, vector L is constant is equivalent to three scalar equations. So we can split or express vectorial capital L, vector capital L as component in x direction, that is Lx is equal to a constant k1, and the component in the y axis along y axis is equal to k2, where k2 is a constant, and the component along z axis, the component of angular momentum along z axis Lz is equal to k3. Let it be equation 7b. Here K1, K2 and K3 are constant. Lx, Ly and Lz are components of total angular momentum vector along x, y and z axis respectively. Therefore, the statement that the total angular momentum is conserved means that each of these three components is also conserved. Equation 7a, that is dl by dt equal to 0 or L is equal to constant, is the rotational analog of equation dp by dt, that is differential of linear momentum equals 0. That means the conservation law of total linear momentum for a system of particles. It has applications in many practical situations, which we'll study in subsequent slides. Let us work out some two examples. Question number 1. Find the torque of a force 7I plus 3J minus 5K about the origin. The force acts on a particle whose position vector is I minus J plus K. Here F is equal to 7I plus 3J minus 5K and position vector R is I minus J plus K. Let us solve it. Given vector R is equal to I minus J plus K and vector F is equal to 7I plus 3J minus 5K. I, J and K are the unit vectors along X, Y and Z axis respectively. We know torque is defined as tau. Torque tau is equal to cross product of vector R and F, that is R cross F. That can be written as, putting the values of R in a determinate form, we get ijk in first row, 1 minus 1 and 1, that is coefficient of vector R in the second row and coefficient of vector F 7, 3 and minus 5 respectively as shown in the figure. And using the knowledge of determinants and solving, we get tau is equal to torque tau is equal to 2I plus 12J plus 10K. That is the answer. Next next question is question number 2. Show that the angular momentum about any point of a single particle moving with a constant velocity remains constant throughout the motion. Answer. Let the particle with velocity v be at point P at some instant of time. We have to calculate the angular momentum of this particle P about an arbitrary point O. So the position vector is OP, velocity is V along x-axis, and the perpendicular from the direction of V to direction of r is OM, and it's the angle between V and R is theta, and the perpendicular distance OM is r sin theta. So the angular momentum is given by the relation vector L is equal to vector R cross M into V. Therefore, its magnitude is mvr sin theta, where theta is the angle between vector R and vector V as shown in the diagram. Although the particle changes the position with time, the line of direction of V remains the same. Hence, OM is equal to R sin theta is constant. Further, the direction of L is perpendicular to the plane R and V. So, plane of R and V is this, and the direction of angular momentum L is into the paper. The direction does not change with time. Thus, the angular momentum remains the same in magnitude and direction and is therefore conserved. With this, we come to the conclusion of section 7.5, 7.6 and 7.7 of torque, angular momentum and rotational motion. In the next lecture, we will take up equilibrium of a rigid body, moment of inertia, perpendicular and parallel axis, and kinematics of rotational motion. Till then, goodbye.